So I'm back with my original configuration, that is 30 fps and 720p, because on 1080 60 1080p 60 frames per second, what fps, or I don't know what it calls. My laptop got stuck, or my video is not uh, video is not playing in order and lag so much. So yeah, and actually I'm kind of feel very sleepy, so just I don't talk very much. So yeah.
In that array, the value of the arrays changes, and all the values in all the slices that are pointing to that array, they also change. We don't always create slices out of an array. We don't have to declare an array and slice from it. We can directly create a slice. Go provides us the ability to directly create a slice, and in the background, Go will create a backing array, and it will give you a slice which points to the array. Okay, and that's how it will work. So this is the syntax using which you can directly declare a slice. You would not have to declare an array and slice from it. You can directly declare a slice, and this is called a slice literal. We are literally declaring a slice in one line. Okay. We have a variable declaration pattern here, with the colon equals to, and here we are saying it is a slice since there is no number in between the square brackets, which means it is a slice. That is the indication. That is the difference between an array and a slice. In an array type, since there is no number in between the square brackets, which means it is a slice. That is the indication. That is the difference between an array and a slice. In an array type, you will find a number, which is the size, and it is part of the type. And in a slice, there is no number. It is a dynamic array. Okay. So this is a slice, and it is a slice of integers, and here we are providing the values during the initialization phase, and here we are printing it. In the same way, we are creating a slice of booleans, so we can only store true and false, true and false. We cannot store any other data type in a slice or in an array. It is a collection of homogeneous data types. In the same way, we can also make a slices of structs. So this is how the syntax looks like. You write a pair of square brackets, then you define the type. In the same way, here we have defined the type. You can integer, boolean, or a struct. If it is a struct, you have to provide the type of the struct, and the type of the struct is this. I. It has two fields, I and b. I is of type integer, b is of type bool. Now, right after, since it is an slice literal initialization of type struct, okay, we have to provide all the values that goes inside this slice of structs. So we can provide, we can follow this pattern. 2 will get assigned to I, and this 2 will get assigned to B. Same way, all the structs are initialized in this slice, and then we can print it. So let's run this and see how it looks like. Okay, and we can see all the slices that got printed here. And this, since this is a slice of structs, we can see all the structs being printed here in the Gauss format. Now another thing is you can also slice from another slice.
Okay, Why it's giving me error? Mhm.
in these slices, and then we can print it. So let's run this. Get this, you have to find the type. You can integer, boolean, or a struct. If it is a struct, you have to provide the type of the struct, and the type of the struct is this. It has two fields, I and B. I is of type integer, B is of type bool. Now right after, since it is an slice literal initialization of type struct, okay, we have to provide all the values that goes inside this slice of structs. So we can provide, we can follow this pattern. 2 will get assigned to I, and this true will get assigned to B. Same way, all the structs are initialized in these slices, and then we can print it. So let's run this and see how it looks like. Okay, and we can see all the slices that got printed here. And this, since this is a slice of structs, we can see all the structs being printed here in the GOS format. Another thing is, you can also slice from another slice. Here we don't have an array here, but you can create more slices out of this slice. Okay. And also we can modify, we can make changes to this syntax. We don't always have to provide the low bound or high bound. We don't always have to provide the start index and end index. We can leave one of them and the other range will be implied. So for this case, we are saying we are slicing from the first index, from 0 to 2. And here we are saying we are slicing from index 1 up to the end. Okay, those things are implied here, and we can run this and see the example how it looks like. So we have 357 for the first, then 35 and 5. Here for this we have 357 because we are indexing from here up to here, from index 1 to index 4. So we are taking 1, 2 and 3. That's why we have 357. From this we have this 3, 5 and 7. This is the value that we have. Then we can slice it again, and when we slice it, we are slicing from the first position, from 3 to the index 2. So 0, 1, 2, and we exclude the 2, so we have 5. We have 3, 5. That's why we get 3 and 5. And here we take this slice and we slice it again, and we are slicing from the first index. So this is index 0, this is index 1. So we are taking the first element is 5 and up to the end, and since this is the last element, we end it here, and that's why we have 5 here. That's how slicing works, and you can slice from an already existing slice. You don't always have to slice from an array. You can also slice from an existing slice. Now in this example, we take a look at lengths of slices. So what we are doing here, we are defining a function called print slice. What it does, it takes a slice of integer as a parameter, and what it does, it tries to print it. And how does it format it? It is taking the length of the slice, and it is taking the capacity of the slice, and it is then taking the slice itself, and it is printing all three of them in this format. Okay, that's what this function does, and we use it here. We create a slice using the literal syntax. We say it's a slice of integer, and we provide all the integer values, and then we do the print. We call the print slice function, which displays the length, the capacity, and the value of the slice itself. The same way, what we are doing here is we are slicing from the start, because we have left the starting index from the start. up to the 0 index, which basically means the length of 0. We don't want any elements because the last element is excluded and we are starting from the start. We have now 0 elements. We don't have anything. We have an empty slice. Okay. In this print statement, we should have an empty slice. Now let's picture this, how it exactly works. So for the first, initially what happens, we have initialized a slice. So we have initialized a slice. So we have a slice here and it has a backing array. But for the sake of this example, let's imagine this is the backing array, because when you initialize a slice literal, then the length and capacity of the backing array is the same as the length and capacity of the slice. So you can imagine this slice as the backing array. Okay, now we have 2, 3, 5, 7, 11 and 13. And these are the slots, is index 0, 1, 2, 3, 4 and 5. Okay. And this is what S looks like initially in this print statement. So for this print statement, what will be the length? The length will be the initial length, which is 6. And what will be the capacity? For a slice literal, the capacity of the slice is the same as the capacity of the backing array. It has a backing array which looks exactly like this, because we initialized a slice using the literal syntax. That's why and that is the reason for the first print statement we get length as 6 and capacity as 6. Okay. And when we print the slice, this is 2, 3, 5, 6, 2, 3, 5, 7, 11, 13, all the elements of the slice. Now moving on. At this point, what happens? What happens is, we are saying we are starting from the start. Okay, we are starting from the start, but we go up till the 0 index. And since the last bound, the higher bound is excluded, we exclude the 0, 1. So in that case, we don't have any elements. So this is an empty slice. But what is the length here? For an empty slice, what is the length? Length is 0. Length is 0. As you can see, length is 0. Because we don't have any elements yet, because the higher bound you mentioned was 0. What will be the capacity? Now, as we know, the capacity is the first element that the slice points to. In this case, it is 2, the index 0, up to the last element of the backing array. And this is the backing array for this slice, and that is the reason we have the capacity of 6. We have capacity of 6, and as you can see, the capacity of 6. Starting from this to this, we have 6 slots. Capacity is 6. Then what happens? At this point, we are saying we are starting from the start. For this slice, this is the backing slice, okay? And this slice points to this. Now what happens? We are starting from the 0, 1, and we are going up till 4. And we are going up till 4. Now we are extending the length. Length was 0 here. And since we have a capacity of 6, we can extend the length. What happens when we extend it? From 0, we go up till 4. Now this is 4, so now we have 2, 3, 5, 7. We exclude the 4th index. We have 2, 3, 5 and 7. These are the elements of this slice. And what is the length here? The length is 4. That is the capacity here. The capacity is still 6, because starting from this, we go up to the last element of the backing array, which is this. That's why the capacity is 6. Okay, and we can see here, length is 4, capacity is 6, and the elements are 2, 3, 5, 7. Now, what happens at this point? At this point, this is the backing array. Now, what happens this? Now here, this is the backing array, and we slice from this slice. We slice from this, but the backing array still remains the same. Okay, this is the backing array. What are we doing here? We are starting from the second index. So we are starting from here. Second index, we include this. We are starting from 5 and up till the last element. Now last element, not of the backing array, last element of slice. When you are slicing, we go to the last element of the slice. Okay, now what is the last element of the slice? Is 7. That's why we have 7 here. Okay, and what is the length here? Since we have 2 elements, the length is 2. And what is the capacity here? Now, as we know, capacity is the first element of the array that the slice points to. What is the first element this points to? This. We start from this and we go up till the end last element of the backing array. Okay, and what is the last element? 13. So how many capacity do we have? 5, 7, 11, 13. That's why the capacity is 4 here. As you can see, length is 2, capacity is 4, and the slice we print is 5, 7. This is how it works. Now, as we already know, in this case, Go assigns the 0 value of that data type. In case of a string, it is an empty string. In case of integer, it is 0. In case of a boolean, it is false. Okay. Now, what happens in this case? What is a 0 value of a slice? What will Go assign in this case? Since we are following this syntax, so ideally, if it is an integer, s's value will be 0. Since it is a slice of integer, what is the 0 value of s? Let's run this and you can see, okay, this is what we get. For this println statement, we are getting s. If you try to print s, it is printing an empty array or an empty slice. The length is 0 and the capacity is 0. So for a 0 value slice, a slice which is declared without an initialization value, the length will be 0, the capacity will be 0, and it will have 0 elements. But the thing to focus here is the value of the slice itself, not talking about length or capacity or the print statement. The value of the slice will be nil. When we try to compare it, if s equals to nil, we get inside and we print this statement because the 0 value of a slice is nil. So now the point here is 0 value of reference types. Reference types are nil. We already know 0 value of an empty string is a string in quotes. 0 value of a boolean is false. 0 value of an integer 0, and 0 value of an array is all the, let's say if it's an array like 4 integer, then the 0 value will be 0, 0, 0, 0. Okay, this is the 0 value of an array with size 4 and type integer. What is the 0 value of a struct? So let's say, okay, let's come here. We have a struct, and here we have a, it's an integer, b is a string. Now, what is the 0 value of this struct? The 0 value of this struct is a 0 and b as an empty string. Basically, in case of an array and in case of a struct, the 0 value is that data structure with all the 0 values of the elements. Because an array is a fixed type with 4 integers, its 0 value 0, 0, 0, 0. In the same way, since a struct has 2 fields with a integer, b string, its 0 value is a as 0, b as empty string. In the same way, we have reference types. What are the reference types do we have? We have functions, we have channels, and we have pointers, we have slices, we have maps. And since we are talking about slice here, the 0 value of a reference type, which is a slice, is nil. This is a very important thing to remember. The 0 value of a slice is nil. Now we saw the first way to initialize a slice, which is the literal syntax. So in this case, we saw that we can declare a slice and we can initialize it like this: a, and we have integer, we have our curly braces, we have 1, 2, 3. Okay, and we saw we can declare and initialize a slice with this syntax, with the literal syntax. We also saw we can declare a slice using var and the name of the slice and the type of the slice. And for this, the value of the slice will be nil, the length will be 0, the capacity will be 0. For this, the length will be 3, the capacity will be 3. Okay, and the value will be 1, 2, 3. We have one more way where we can initialize a slice or declare a slice is using make. A make is a function, a predefined function. Make, M-A-K-E, it's a predefined function given by Go for initializing reference types. This is something to remember, initializing reference types only. Okay, we can use make to initialize channels, to initialize slices, to initialize maps, all the reference types that we can use make to initialize, because we have a reason to use make instead of using the literal syntax. Why are we using make? So let's see that in this example. When we initialize a slice using make, what happens? So what we are saying is we are initializing a slice of A, and we are saying make a slice. Make, you can take it as semantically whatever it reads like. You're saying make a slice of integer. You're saying make a slice of integer, with the second argument. The second argument to the make is the length. This is how make's signature looks like. Make, it takes three things. First is the type, and what are we providing in the type? We are providing, it's a slice of integer. It is a slice of integer. Since we also use make to declare and initialize maps, to declare and initialize channels, so we have to explicitly say that it is a slice of integer. First parameter, first argument is a type. What is the second argument? Is the length. You can say what is the length of this slice going to be. Okay, now we already know that slices are dynamically sized. We will see how the dynamically sized mechanism works, but initially you are saying the length should be 5. Okay, we are saying the length should be 5. Now there is a third parameter. Called capacity. We already know the mechanism of capacity. We still have not gotten the exact use case of capacity, but we'll get it soon. Now the third parameter is capacity, but by default, if you don't provide the capacity, it will take whatever the length is. So in this case, the capacity will also be 5. So now we have a print slice function. What we are doing is we are printing the length, the capacity, and the slice itself. Okay. Now in the first case, what should it print? Now that we have the theory, before you run the program, we can visualize it. For the first statement, for the first print, what we are doing, we're printing A. At this point, what's the state of A? The length will be 5 and the capacity will be 5. Okay, and now let's move on to B. What's B? Okay, now we are using make. What is the type? The type is a slice of integer. What is the length? Length is 0. What is the capacity? The capacity is 5. Now you cannot provide a length that is greater than capacity. That is an error. Okay? That's something to remember. The capacity will be always same or greater than length. The capacity cannot be less than length. Okay? Since capacity represents the size of the backing array, so capacity will always be the same or greater than length. Okay. Now this is the state of B. Now when we call print slice, what should it print? It should print length is 0, capacity is 5. Also for A, I forgot to mention what will be the actual slice print. In case of A, since the length is A and it is a slice of integer, ideally it should print, A should print 0, 0, 0, 0, 0. 5 zeros, because the length is 5. What should B print? It should print an empty slice, because the length is 0, so we don't have any slots to initialize it with. In case of A, the length was 5 and the type was integer, so the 0 value of a slice of integer with length 5 should be 5 zeros. Okay. Now C. Let's move on to C. We have C here. Now we are slicing C from B. What are the properties of B? You have length 0 and capacity as 5. Okay, and what we are saying, we are saying for C, we are saying starting from the first index. The first index is of course 0. Is slice from first index or second index. We sliced from the very first 0th index. That's why the capacity does not change. The capacity only changes when you slice after the first index, after the 0th index. Any index which is more than 0, if you slice from there, then the capacity reduces. But it does not reduce when you slice from the end. Okay, that's a mental model you don't really have to understand or memorize, but you'll get it after you use slices a little bit more. Now, what is the capacity here? Capacity is still 5 because we did not slice after the 0th index. We sliced from the 0th index. Now, what is D? For D, what we are saying, from C, starting from the second index, it has only 2 elements. We don't really have index 2, but we have capacity of 5, so we can slice up to 5 elements, because the capacity is 5. Okay, what you're saying, 2 to 5, since 5 is excluded, we print 2 3 4. Okay, print 2 3 4, but there are no values here, so we go to 0 value. What are the 0 value of integer? We have 3 zeros. 2 3 4 for index 2, index 3, index 4. What is the length now? Length is of course 3. What is the capacity? Now, since we sliced from the start, we did not slice from 0, we sliced from 2. Now the capacity decreases. Now, so 0 1 2 3 4, we had 5 indexes. Since we slice from here instead of here, this is gone. Now we have 3. The capacity is 3. From 5, since we sliced from index 2, now the capacity is 3. Now let's try to run this program. As you can see, for the first one, length is 5, capacity is 5, we have 0 0 0 0 0. For the second one, the slice is empty, length is 0, capacity is 5. For the second one, we have 2 zeros, third one we have 3 zeros, with the length 3 and capacity 3. As expected, the same values that we saw in our figures. Another thing to know is we can have 2-dimensional slices. A slice can contain other slices. So in this case, what we are saying, we have a slice which is a slice of another slice, and that slice is a slice of string. So we are initializing with each slice, which is a slice of string, and we are providing different strings. So this is how you declare and initialize a 2-dimensional slice. We have 2-dimensional arrays in a lot of languages, pretty much every language. In the same way, in Go also we have 2-dimensional slices, and if you print this, you should have some kind of matrix. And as you can see, we are printing a game of tic-tac-toe. Okay, and we can change the values using the x index and y index in different positions. That's pretty much all there is to it in 2-dimensional slices. Whatever your intuition, whatever it sounds like. Initially, I said that slice is a whatever it sounds like. Initially, I said that slice is a dynamic array, and and dynamic means we can extend a slice, extend its length, extend its capacity, and add more elements, remove elements, all the dynamic properties that are useful in a real world application. That's why we use slice more often than we use arrays, because of their dynamic nature. Now, how do they work? How do we actually add more elements to a slice after we declare it? So this is how it works. This is the syntax. We declare a slice and we are using the var syntax. So at this point, the value of the slice will be nil, and if you print it, it will be an empty slice, and the length will be 0, the capacity will be 0. Okay, and if in the first print statements, we should get the length 0, capacity 0, and empty slice. What happens here? We are saying we are appending to this slice the first argument. So append is an inbuilt function in Go, and it takes multiple arguments. The first one is the slice, which we want to append to the slice, and we are providing s here. What is the second argument? This is the element, the new element that we want to append to the slice, or that we want to push to the slice. And here the new element is 0. What happens? We had a slice which looked like this, with length 0 and capacity 0. Append does a lot of things, a lot of calculations behind the scenes, but on a high level, the reason we are provided with this function, we are provided, first thing, it takes the slice that we want to append to, takes the existing slice. As you can see here, we are providing the existing slice s. First thing, it takes the slice, and in the second parameter, it takes the new elements. Okay, and it also takes a lot of, you can also pass more arguments into the function. It is a variadic function. Go has a concept called variadic function, where a function can take any number of arguments. Okay, now append is a variadic function. You can pass any number of elements in the after you pass the slice. Okay. Now second, it can take one element like it is taking now, 0, or it can take any number of arguments. It takes two things. What it does is, first it checks the length and the capacity of the existing slice. Now what is the length and capacity of our existing slice? It is length is 0, capacity is 0. Now if that is true, and since we are trying to add more elements into that slice, but we don't have the capacity for it, okay, the backing array that we are using in the slice, the array does not have enough capacity to it. So what append does, it assigns another memory location, another backing array whose length is 1 and whose capacity is 1, and it returns that as a return value of append. Now you are assigning it to s. Now what happens? S has length 1 and capacity 1. What happens here after that? Then at this point, S has length is 1, capacity is 1. Now this is what S looks like as of now. Now what we are doing, we are calling append again, and we are passing 1. We want to append the number 1 into this slice. We pass it, and append checks the capacity of the existing backing array, and since the capacity is 1, we are trying to insert another element, so we need at least 2 slots. So for that, append finds another memory location and it assigns another backing array. Now we have length as 2 and capacity as 2, and this is what the new slice looks like, and this is what we return, and we assign it to s again. Okay. Now at this step, this is what it looks like, and since we are inserting 3 elements,
This
now
is an
append
announcement video
follows
for a very
different
interesting
algorithms to resize the existing slice. There are a lot of internal details there, but on a high level, there can be 2 situations. Either you are appending 1 element, or you are appending a number of elements. You are using the variadic parameter. Now to understand that, let's go to our notepad. Now as I said, there can be 2 cases. One, you are inserting 1 element, or 2, you are inserting variadic element. elements. Now there are a lot of internal details, as I said, for resizing the slice inside the append function. Now we can actually take a look at how the code looks like, which resizes the slice using the append function. Now if we go here, this is actually the code which does all the resizing of the slice and all inside the Go programming language. You can see there are a lot of internal details here, and there is actually a function which is next slice capacity, the function to calculate what is the capacity of the next slice. You can see there is a threshold of 256, length of 256. If it is smaller than that, it doubles it, otherwise it does something else and all. So there are a lot of things happening here, a lot of internal details. But to have some idea about how the algorithm works, we can take a look at some of these rules. So the first rule is, if it is a single argument, if it is a single element, first thing we know, we use append to resize, to add more elements to a slice. So let's say we have a slice with length 0, capacity is 0. We have an empty slice. Now if we call append s equals to, we take s, we pass it to append, and we add another element, let's say 1. What happens now? What append does in this case, since this is a single element, what append does, since the capacity is 0 at this point, it checks the size of the element. Since this size is 1, so append finds another memory location for the new backing array, and it finds the pointer to that, and it assigns that new pointer, and that array will have a length of 1 and a capacity of 1. The first time we call append on an empty slice. What happens the second time? Now this is what the slice looks like. We have 1 here, length is 1, capacity is 1. What happens if we call append again? We call append again with s and number is 2. At this point what happens? It finds, since the capacity was 1, we are trying to insert another element, so we need the capacity of 2. So it finds another memory location for the backing array, and it assigns the pointer to that, to the new slice, and now the length is 2 and the capacity is 2. We'll soon notice the pattern here. Again, let's try to append another element. Append s, and this is what the slice looks like in the previous step, 1, 2, now s3. Now at this step, what append does, since we have capacity of 2 and we are trying to insert another element, now we need slots for 3 elements. Now what append does, it tries to find another memory location for the backing array, and the length will be now 3, but the capacity will be the double of the previous one. So previously we had capacity of 2, now we will have the capacity of 4. Okay, so let's do one more time, then we'll see the pattern. Let's call append, then s, then we pass 4. Okay, and this is what it looked like, 1, 2, 3, and we call it once more. Now we had capacity of 4. Now we are trying to insert another element. We only have 3 elements as of now, so the append does not do anything. It has enough capacity to assign one more element. So now length will be 4, capacity will be 4, and this is what the array slice will look like, 1, 2, 3, 4. Now what happens here? One more time. Call append, call s with 5. Now we have 4 elements, we have capacity 4. We are trying to insert one more element. Now we don't have the space for that. Now what append does? Now the length is 5, capacity is 8. It is 8, and this is what the slice will look like, 1, 2, 3, 4, 5. Now we can see the pattern. When we are trying to insert single elements, append will try to double the capacity every time there is no space. It will try to double the capacity up to as we saw here, up to the threshold is up to the length is 256. After that, it will, as it is written in the comment here, it will, instead of 2xing, it will go in the 1.25x speed. It won't double it. It will go in the speed of 1.25. It will only double it up to the length is 256. elements. After that, it will go 1.25x speed. It won't double the capacity. That is an internal detail. Now, that is one pattern. And if you want to see an example for that, here we are declaring a slice with 0 value, and we are starting a for loop. And in every iteration, we are appending the index into the slice. And then we are printing the length and the capacity of the slice in the print statement. Now let's run this, and we'll have a fair idea how the append works behind the scenes. Okay, now if we expand it, okay, let's focus here. Let's focus what's happening. In the first iteration, the length and capacity was 0, so append made length 1 and capacity and 1, and this it is 1. In the second iteration, it inserted another index, and now the length is 2, capacity is 2. In the next iteration, when it was inserting, let's say first 0, then 1, then 2. When it was inserting 2, obviously the space was not enough, so it doubled the capacity. From 2, it went 4. Okay. Now, in the next iteration, it has enough capacity. It has the capacity of 4, so it can store one more element. So that's why we can see the capacity does not change until this. The length is 4, the capacity is 4. Okay. Now, in the next iteration, when we are trying to insert the index 4, now it does not have the storage anymore. Now it needs to increase the capacity again. What it did, it doubled the capacity again. The append function doubled the capacity of the internal backing array. Okay, that's what's happening here. Now we can insert 4 more elements. Up until this, we had 4 elements. Now it doubled the capacity, so we can insert 4 more elements. Now at this point, we have 8 elements and we have capacity 8. As you can see, the length is 8, the capacity is 8. Now append has to assign a new backing array. It has to increase the capacity again. Now it doubled it. From 8, it went 16. Now after this, we can insert 8 more elements. We had 8 elements, it doubled the capacity, and now we can insert 8 more elements without append having to increase the capacity, without append having to assign a new memory location. It can store the elements in the same memory location. So as you can see, length is 10, 11, 12, 13, 14, 15, 16. Now when the length and capacity matches, the capacity is doubled again. So this is the pattern you can see. Every time length and capacity become same, in the next append call, the capacity doubles. Okay, that's the formula. Every time length and capacity matches, in the next iteration, append will double the capacity and it will assign a new memory location for the slice, for the new backing array. And now why am I trying to explain these internal workings of how append actually works? What is the need of it? Because most likely this is how you'll use. You have an slice and you call append again and again. Every time you have to add more elements. You never have to think about what is the capacity, what is the length and all. Those are internal details. You will never actually have to explicitly think about the capacity and all. The append handles all those details behind the scenes. But the reason I explained it, the reason I explained how it works, what are all the things that happens behind the scenes every time you call append, every time the length and capacity matches, is because let's take an example. Up until this, let's print the value of this. Let's clear this. So go run main node go. We have length 0, capacity 0, and there is an empty slice. Now when we try to append another element to this and we call print slice again, now what happens? Let's run this and we can see that length is now 1, capacity is 1, and we have 1 element in the slice. What happened behind the scenes? Append checked the capacity and it realized the slice, the backing array, does not have enough capacity to store 1 more element. So it searched for another memory location and it found another location for the new backing array, and the new backing array has capacity of 1 and length of 1. And as we saw earlier, if you call append again, it will do the same number of steps again, and the length will be 2, capacity will be 2, and it will keep reallocating. It will keep reallocating and finding new backing arrays every time you call append. It will try to double the capacity and it will try to do all those optimization steps to resize the slice, and all these internal calculations will keep happening when you start with a slice of zero length and capacity. But let's imagine there is a scenario like this, when you know beforehand that you want to append to this slice 5 times. You know this information beforehand, and in this case, if you initialize with an empty slice with length 0 and capacity 0, and you run the iteration, it will work. It will definitely work. And if we can run this, and when we run this, we can see that it started with length 0, capacity 0, then in the next iteration capacity is 1, next capacity is 2, then capacity is 4, and then the capacity is 8. Okay? And every time you know that length and capacity matches, every time length and capacity matches, in the next iteration the append has to do all these internal calculation. It has to find a new memory location, it has to find a new backing array with a double the capacity, and all this extra work. Every time reallocation happens because of the shortage of capacity. Now, if you know the maximum length that this slice can have, what you can do, one optimization that you can do to prevent append from doing all this extra work is this. Instead of initializing s like this, what you can do, you can remove this and you can use the short declaration form, and here you can use make. And you already know, if you use make, you can define a length and an optional capacity. Let's say we want length as 0 because we don't want pre-filled zeros inside the slice, because if you define length as 5 and capacity is 5, it will pre-fill all those spaces with empty zeros. We don't want that. That's why we are saying length is 0 but capacity is 5. Maximum we'll have 5 elements, but for now give us an empty slice. What happens if you run this now? Now, as you can see, the capacity from the first iteration is the capacity is 5, and we keep appending to it, and up until the last iteration the capacity remains the same, because we already knew that we are going to append 5 elements max, and we just prevented append, the function, inbuilt function append, from doing all those extra calculations every time there is a shortage of space. So this is something you have to remember, that we'll use, especially this syntax, that if we know beforehand what is going to be the maximum size of a slice, we can use this syntax to pre-assign a capacity beforehand to prevent append from doing all the extra work every time it runs out of space. Go provides us one more construct to loop over slices. We have a traditional method where we use a traditional for loop. We initialize a variable, we put a condition, we do increment in each iteration, and then we can print the index and the value using the index access method. This works. But Go provides us another construct. It's called range, and using range you write a for, and with each iteration Go returns 2 values. First one the index, and the second one a copy of the value, not the value itself, a copy of the value. This is something you have to remember. If you make any change to this value here, it won't show up in the original slice, because this one is a copy in each iteration, and you can access the value of I and B here. And if you try to print this, you'll get this 0 1 2 3 4 5 6 7. And if you don't want to use the index, then you can use the underscore, and if you don't want to use the value, you only want the index, then you can leave it apart. And if you want to take a look at some examples of slices in real world apps, then we can index, then you can use the underscore, and if you don't want to use the value, you only want the index, then you can leave it apart. Okay. And if you want to take a look at some examples of slices in real world apps, then we can take a look at Fider. And you can see we have a lot of use cases. Here they are using the slice literal syntax to directly declare and initialize a slice in the same line. We have some make based syntax to initialize a string slice with length 31 and capacity 31. And similarly, there are a lot of use cases everywhere in the code. Slices are one of the most common used data types in Go, and you will see a lot of examples everywhere. Okay, here we have a range over slice. They're accessing the value of title in each loop, and they're doing something with it, and a lot of examples like that. And the next data type that we have is maps. Go offers a implementation of the data type hash map, which are also called dictionaries, hashes, hash maps in other languages. Go also has a similar implementation, which is called map. And map, a typical structure of a map is it has a key, which is mostly string, but you can also use other data types. As the key, and it has a value, and inside the value you can store anything. Okay, maps keys has to be comparable. So comparable basically means they have to satisfy the equality operator, so that the map keys can be compared with each other. They have to have that property. That is one restriction of maps keys. And in the value you can store anything in a map. Okay, and usually we use map whenever we have a use case where we want to find things quickly. That's the mental model you should have. A lot of people get confused with when to use struct and when to use map. Struct is your typical use case whenever you want to store something, whenever you want to parse data from a JSON. A lot of use cases. In pretty much 70% of the time, we use structs. Struct are for storing values, for efficient storing values in the format of Go's native data types. In map also, you can store values, but we use maps when we want to find things quickly. Okay, because maps have the lookup time of one, lookup time and adding time and deleting time. All this, it's a very efficient algorithm to look up things and to add things and to delete things. That's the reason we use hash maps or maps in Go to perform those kinds of tasks. Now let's understand with an example how they exactly work. So what are we doing here? We have a struct, there's a type struct, and it has two fields. One is lat and second is long, one for latitude, one for longitude, and both are of type float64. Okay, this part we already know. Then we are declaring a variable in the package level with using var syntax. The variable name is m and it is of type map. A map with key as string and value as vertex. So whenever you are declaring a map type, you have to explicitly say what is going to be the type of the key and what is going to be the type of value. Now here we declared a map. Now as you already know, map is a reference type, and every reference type has the zero value of nil. So at this point, m's value is nil. Okay. Now here what we are doing, we are ignoring whatever the zero value is. We are using make. As I said, every reference type can be initialized with using make. So we are using make to initialize a map. We are not providing any length, capacity and all. We are just initializing a map using make. Then using this index based syntax, we are storing a struct's instance. A struct's instance, a struct of type vertex. We are storing this struct in the key bell labs. Okay, this is how you store things in a map. And then we are printing it. And if you run it, we get the value of the struct. Okay, that's how maps work. You initialize a map, you store things in the keys, and you can access them using this index-based syntax. This set and get pretty much looks the same way. Now there is another syntax of initializing maps. Instead of using make, you can also use the map literal syntax. Map literal syntax basically means you just write the type and you provide the initialization value right away in the same sentence. So we are saying we are declaring a map whose key is string and the value is vertex, which is of type struct, and we are providing the keys and the values in the same line. Okay, this is another syntax to initialize maps without using make. How do you manipulate values and keys? Syntax to initialize maps without using make. How do you manipulate values and keys? How do you manipulate keys and values of a map? We have some of the features provided by Go. As you know, we can initialize a map using make. And also, one thing to remember when using maps are you only have two ways to initialize maps. First, you can use the make syntax, or you can use literal syntax. Third, if you try to initialize a map using var, which we do with other data types like integers, strings and slices and all. If you initialize a map, declare a map using var syntax, and if you try to assign a key in that map, then you will get an error. You will get a panic. You only have two ways of declaring a map. Either use make syntax or use a literal syntax if you know the initial values already. Okay, we can actually see this. In this example, as you can see, I have declared a map using var syntax. Okay, as we typically do with other data types like slices and integers and booleans and strings. I have declared the map using var syntax, and then I am trying to assign a key to the map. Since it's the keys of type string and the values are of type integer, I am assigning key 1 the value of 9. And then I am trying to print this. Then what happens if I try to run this? We get a panic. We get an error that assignment to entry in nil map. Since using var syntax declares the zero value of a map, and the zero value of a map is nil. That's why we get this error that assignment to entry in nil map. What can we do in this case? We have two choices, as I said. Either we can do this, we remove the var and we do short assignment, and then we use make, and then you do this, and then we try to run this. Then we get the appropriate behavior. We have a map and the key has the value 9. We have one other choice. We can do this if you don't want to use the make syntax. We can write the type, then we can provide a curly braces. This is the literal syntax. Okay, and if you try to run this, we get the similar behavior. So as I said, when using maps, either use make or use the literal syntax. Those are the two choices that you have. Never use var to declare a map unless you know exactly what you're doing. Okay, now we have this example where we are looking at some examples of manipulating the keys of a map. Now here we initialize a map using make, and since we are using make, we are safe to assign keys to the map. Now we are assigning a key answer, and we are assigning the value 42. Now we are assigning this another value to the same key, and let's try to run this, how the program behaves up to this point, up to the point here, and let's see the behavior. Now if we run this, so first we have the value 42 because we assigned 42 here to the key answer, and in the next print statement we are assigning 42 and we can see the value 42. Then what happens? We have a predefined function called delete, and using this we can delete values from a map for a particular key. So when we delete a value and then we try to print the value for that key, we'll get the 0 value of that type. Since it's an integer, we are getting 0 here. Now the question here is, how do you know that whether this key answer has the value of the number 0 or the value is absent, the value does not exist? That's why the Go language is giving you the default value 0. How do you differentiate between the absent value and the 0 value? That is the question. So for that particular use case, Go provides this construct. You can try to access this value of a map using this syntax, the index space syntax, which returns two values. The first one is a value. If the value exists, then you'll have the value here. If it doesn't, it will have the 0 value here. Then it also returns a boolean, and you can name it anything. The convention is to name it OK, so that other engineers are also aware that you're checking the existence of this value. Now we can, if the OK is true, then we'll know that the value exists, and whatever the value, even if the value is 0, we know that it exists and that is meant to be the value. It is not an absent value, it is not a default value, that is meant to be the value. 0 is the value of the key answer. If it is false, then we can ignore the value and we can proceed further with whatever the expectation is. We can know that the value is not set for this key, and that's pretty much all about maps. We can do other things with a map. For example, let's say we have this, and let's move this, and what if we want all the keys and values of a map? So we can use the range construct that Go provides to loop over slices that we can use for maps also. So let's say we write for, in the first result it will give us the key, then it will give us the value, and in the short declaration after that we write range, and we want to range over m, which is a map, and here we can print this mmd.println, we can write key comma value, and if we run this, here in the last print statement, as you can see, the key is answer and the value is 42, and using this we can range, we can loop over maps, and we can access all the keys and values. If you don't want the key, you can use the underscore identifier here like this if you only want the values, and if you only want the keys, then you can get rid of that part. Now this is how you iterate over a map. Now another concept that I want to mention here is, let's say there are some confusions when you're starting out, that when to use map and when to use structs and all. So maps and structs have a lot of differences. For example, you cannot do this with a struct. You cannot loop over all the fields of a struct, because struct is a static type in Go. You already know all the fields and all the values of a struct somewhere. It is already written. You don't have to loop over it. That is the first difference, that you cannot range over structs, but you cannot range over, but you can range over maps. Second, all the values inside a map like this is not a variable. This does not have a fixed memory location. You cannot use this to initialize a pointer, because this does not have a memory location. On the other hand, every struct field has a fixed memory location, and you can use that everywhere, and that memory location will be fixed, because map internally uses hashes and buckets and a lot of internal algorithms to hash and to do lookups and to add keys, remove keys and all. So they don't have fixed memory locations. The memory locations keeps changing as we add more keys and more values. That's the reason the memory location of maps are not fixed. The third thing is also this part. When we are iterating over maps, the order in which we get the keys are not fixed. They are intentionally randomized so that you don't depend on the order to be the same. If you want the order to be the same, you have to explicitly sort the keys yourself. That's also something to remember about maps. And coming back to this, another difference between map and struct is just the use case that we use structs to store data. That is a very oversimplified definition that I have come up, but this is the idea on a very high level. And we use maps to look up. That's a mental model you can use whenever you want to differentiate between maps and structs. So let's go and take a look at what some real world maps look like, how people use them. Then here you can see there are a lot of use cases maps people are using in all for parsing random JSONs into structs and mapping HTTP headers there, because HTTP headers can be of any type, right? There can be a lot of different types of headers and you don't know all the types. So in those scenarios, you cannot use a struct. You have to go with a map, because you want to assign any string and for the key and any string for the value. There is one perfect use case for maps that we typically use for, and there are others for whenever you want to parse any kind of JSON into a Go data type, then you can go with map if you don't explicitly know the keys and values of that JSON. In that case, you can unmarshal it into a Go map, then you can access it. Okay, so there are a lot of different use cases for maps. Another concept after that I want to cover is, in Go, functions are first class citizens, and by that I mean there can be anonymous functions also. So here we have a function declaration which does not follow the typical function declaration that we have here. Here we have the func keyword, then we have the name of the function, then the curly braces start. We don't have the same structure here. What you're doing, since functions are first class citizens, you can assign a function to a variable right inside any function. So what we are doing here, we have a variable, we are using the short declaration form, and we are assigning a function to that. What this function does, it takes two parameters x and y, which are of type float64. It returns the same type float64, and it actually does this math calculation. It does x into x plus y into y, and it calculates the square root of that and returns it. This is what this function does, and we are assigning this function to this variable. Now we can use this variable's name to perform the calculation. We can use this variable as this function, and as you can see here, we are calling this with two arguments 5 and 12, and this will be x, this will be y. Okay, so this is one of the features of functions being first class citizens. You can assign functions, you can assign anonymous functions to variables. Now the second thing, we have a function here. We have a function here which takes another function as a parameter. We can also do that because functions are first class citizens in Go. We are taking a function as input, and what this function's signature is, it takes two float64 and it returns one float64. And if you see, this signature matches this signature. We don't have to write the name of the variables here because this is just a signature of the function. Okay, and this is used as a parameter of another function, and in this case we don't have to write the variable names. Okay, it takes another function as a parameter and returns a float64 value, and in the function execution, what it does, it uses this function to do some calculation with 3 and 4, and it returns the value. Okay, and because of that, because it takes any function and it passes 3 and 4 inside that, that's why now we can use any function whose signature matches this. So for now, we have this function whose signature matches this. We can pass the hypot, this function, inside into this function compute, and we will get the result. The same way, we have an inbuilt function which is math.power, which has the similar signature. As you can see, math.power has x float 64, y float 64, and returns a float 64. Since the signature matches, we can also pass this function inside this, and if you try to run this, we'll get expected results. We have a print statement for this line, then we have this line, and then we have this line, and this everything works in a very smooth manner. And this is a very nice feature of Go, and we can do a lot of composition by passing functions inside other functions, and a lot of other nice feature called we can pass functions into other functions. Go provides another nice feature called closures. Now, if you are a JavaScript developer, you are coming from a JavaScript background, or any other programming language which has the same feature of closure, which I'm not aware of. I'm aware of JavaScript. Then you'll get it. It works exactly the same as other languages, the same as JavaScript, the same way closure works in JavaScript. But if you are a beginner and Go is your first programming language, or you are coming from a programming language which does not have the concept closure, then I would say don't take it too seriously. Don't try to understand everything around it. Just know that this nice feature exists and they are used in a lot of places, in a lot of libraries. You might not use it explicitly, that you won't think like, now I'll use closure for this, but closures are used implicitly in a lot of places. So just know the concept that it's there, and it's not a big deal if you don't understand it right away. Now, this is how it works. This is how closures work. We have a function, and this function returns another function, and this function has access to the variable of the outer function. It has access to sum. Now, because of that, even after this function returns, it has access to a state called sum, which it can keep using. And let's use this example to understand how exactly this works. So let's first run this. Okay. We have different iterations. Let's go through the iterations first. Now, first, we are initializing two variables by calling these two functions. The result of this will be assigned to this, the result of this will be assigned to this. Okay, and the positive, and both of these are different functions of this instance, this type, which takes an integer and it does this calculation with sum and it returns the sum. Now, what happens in each iteration? We come inside, now I equals to 0, and we call this function, the positive function, with I. Since I equals to 0, sum equals to 0, sum plus I, which is 0. So here we see 0. And in the same way, in the negative call, we are multiplying I with -2, and we know multiplying anything 0 is 0. That's why we are also getting 0 here. In the next iteration, now here i's value is 1. Before that i's value was 0. That's why I got 0 0. Now i's value is 1. What happens now? It comes inside, it calls this function positive of I, and then we go here, x is 1. Now sum plus 1. Now since sum is 0, sum plus, in the negative call we are multiplying I with -2, and we know multiplying anything with 0 is 0. That's why we are also getting 0 here. In the next iteration, now here i's value is 1. Before that i's value was 0. That's why I got 0 0. Now i's value is 1. What happens now? It comes inside, it calls this function positive of I, and then we go here, x is 1. Now sum plus 1. Now since sum is 0, sum plus 1 is 1, and return sum. So now this is 1 for this part. Now for the negative part, we -2 into 1 is -2, and -2 is here. -2 plus 0 is -2, and then we see -2 here. Okay, that is this iteration. Now in the next iteration, i's value is 2. We come here, we call positive with the value 2. Now what is the value of sum? Now the surprising part is sum's value does not start with 0 here. Sum actually remembers the previous call, and it, because this positive is the same instance of calling this function, it will remember the state of sum across different function calls. That is what closure means. Closure basically means if we have a scenario like this where an outer function returns an inner function, then that inner function will have access to the outer function's variables even after the outer function returns. Okay? And because of that, the inner function can use this as a state across different function calls. That's the reason in the next iteration, when i's value is 2 and we pass 2 inside positive call, now in the previous iterations sum's value was 1, and it remembers that. That's why 1 plus 2 is 3, and we see 3 being printed here. That's what closure basically means. It's not a concept that you will explicitly use everywhere, but it's still an important concept, and it's used in a lot of places, and it's good to have the knowledge that how it works or it exists basically. Now Go provides a feature called methods, which allows us to assign functions to types, any type. It can be struct, it can be integer, it can be string, any type, any custom type, as long as that type is defined in the same package. That is the condition that we have to match to assign methods to a type. Now we'll typically see types being assigned to structs, but there are also use cases of types being assigned to user-defined types, like custom types that take from integer or strings and arrays and all. Okay. Now how does it work? How do methods work? Let's first look at the syntax. We have a struct here, which is whose name is vertex. It has 2 fields, both of type float64. Now in the next line, we are defining a method on the type struct. What it does is, this part is the same as a function declaration. Okay, if we had a function called abs, then this is what it would look like. It would have a name, it would have a braces, and then have a return type and the execution statements. This is the typical function declaration. But a method is different from a function in a way that before the name of the function, we have the receiver. This part is called the receiver, and this type, and whichever type this matches, then we will say that we are defining a method called abs on the type vertex, because in the receiver we have the type vertex. That's how we assign a method to a type. That's about the syntax. And then we have here available v, which is of type vertex, which is a struct, and this is an instance of the struct, not the type itself, but a concrete instance of the struct. And usually we write a short variable because we'll again and again have to access that, but you can make it readable also. It is not that important. And using this, we will have access to the fields of the structs here. You have access to the fields of the struct, whichever struct we are calling this method on. Now, in order to see the use of this here, we are declaring a variable v, and please don't confuse this with, this is a parameter, this is a variable declaration in another function scope. Now we are declaring a variable which is of type struct, a struct called vertex, and we are assigning 3 to x. Before. Now, in the next line, we are defining a method on the type struct. What it does is, this part is the same as a function declaration. Okay? If we had a function called ABS, then this is what it would look like. It would have a name, it would have a braces, and then have a return type and the execution statements. This is a typical function declaration. But a method is different from a function in a way that before the name of the function, we have the receiver. This part is called the receiver. And this type, and whichever type this matches, then we will say that we are defining a method called ABS on the type vertex, because in the receiver we have the type vertex. That's how we assign a method to a type. That's about the syntax. And then we have here available V, which is of type vertex, which is a struct. And this is an instance of the struct, not the type itself, but a concrete instance of the struct. And usually we write a short variable because we'll again and again have to access that, but you can make it readable also. It's not that important. And using this, we will have access to the fields of the structs here. We have access to the fields of the struct, whichever struct we are calling this method on. Now, in order to see the use of this here, we are declaring a variable b, and please don't confuse this with, this is a parameter, this is a variable declaration in another function scope. Now we are declaring a variable which is of type struct, a struct called vertex, and we are assigning 3 to x, we are assigning 4 to y. Now v is a struct, and now what we are doing, now since v is a struct of type vertex and we have defined a method on the vertex struct, now we can call the method using this syntax. We can do a dot and then we can call the method name ABS. And when we do this, this instance of this struct will be passed to this function, this method, and in this place where we have v, this value will be passed, this instance of the struct where x's value is 3 and y's value is 4. So this is how it works, and if we run the program, we can see 5, because after the calculation the answer is 5. Now instead of that, what if we comment this out and we define another function which works pretty much the same as this one, but it does not have a receiver, it is not a method on a type, it is a normal function. And how do you call a normal function? We just pass the struct inside it. And what if we call this? We have the same result, 5. Now what is the difference? Why did we define a method on a struct? Now there are a lot of reasons for defining methods. So if you come from a object-oriented language background, then you can relate with the idea of methods with class methods. You have a class and there are methods associated with it, and every time you call a method on an instance of a class, then you have that method limited to that scope. So if you come from an object-oriented background, then it will be a pretty clear idea to you that what is the clear distinction between methods and class methods. Now using methods, we can assign some behavior to a type so that it is very clear that we have a type and this type has all these behaviors, all these capabilities. It forms one kind of a documentation, and it also has some readability advantage and a lot of other advantages that methods offer. But on a high level, you can simplify it to that level, that it offers some advantages over using normal functions. Now, as I have already mentioned before, that we can use methods on other types also. So we have a type here, type.
Just taking a small break. I will be back.
Any name, we are saying my float. This is the name of the type, and it is of type float64. So this is how we can define custom types, user defined types in Go. We have a custom type here, and we can define methods on this type also. It does not always have to be a struct. We can also define methods on custom types, any user defined type, any type in Go. Okay. And this is how it works. You define a method and it takes a receiver, and every time you call an instance of this type, so f is an instance of this type, we are initializing it, and when we call this with ABS, it passes this instance to this receiver and we get the result. So the idea is you can define methods on any type, any concrete type. We'll come to interfaces, but you can define methods on any concrete type in Go. Now when you are defining methods on a type, the receiver, this part, it can be a value which looks like this, or it can be a pointer which looks like this. This basically has a star in front of the type. Now what is the difference between the two? If you have a value, then whatever calculation, whatever change you do here, it won't be reflected in that instance of the struct that you call the method on. Okay, every time you call a method, you pass this instance of the struct into the receiver. Okay, that's how methods work. You initialize a struct, and whenever you call this method, this instance gets passed into this receiver. Now if it's a value receiver, then whatever change you make to this variable, which is of this type struct, this is an instance of this type, it won't reflect in the original instance. But if it is a pointer receiver, then whatever change you make to this struct, will reflect on the original instance. So that is the difference between a value receiver and a pointer receiver. Now if we run this program, we get 50. Initially we were getting 3 and 4. By passing 3 and 4, we are getting 5. We got 5 in the previous result, but we used this function scale, this method scale, which actually changes the fields of the structs, and then when we call ABS on it, we got 50 because we scaled it by 10. So this method actually changed the value of these. Two fields. That is the difference between a value receiver and a pointer receiver. Now at this point we can see another advantage of using methods instead of functions. Why do we have methods and how are they different in behavior when compared to functions? Now we have a function which pretty much works exactly the same as the previous methods. What happens if we remove this star? What happens if we say that v is a value? Now we will get an error here which says cannot use %v value of type pointer vertex as a vertex value. We cannot assign a pointer to a function which is expecting a value. Now in order for this to work, we have to also remove this. Now we are passing the value, but now the behavior also changed. If we run this, we'll get 5 instead of 50. Now to see the differences between methods and functions, we have one method here with a scale method defined on the struct. We have one function here, normal function, which is not a method. And here what we're doing, we are initializing a struct of type vertex and we are calling the method scale, and here as you notice it is expecting type pointer, but here we are calling the method on a type value. We did not have to do this. We did not have to do this. V dot scale. We did not have to call the method with a pointer. But in the same way, when we are calling a function, if we remove this, if we pass the value, then Go will throw an error. That cannot use variable of type vertex as a pointer. But in case of a method, Go automatically did the pointer indirection. Go automatically passed the pointer to the method instead of the value. So basically, Go internally did this, converted this into this before calling this method. That's a nice advantage of using method, that you do not explicitly have to think about whether the signature of the receiver matches the instance that I am calling the method on. It can be a value and the receiver can be a pointer, and it can be a pointer, the receiver can be a value. It will do the pointer indirection and it will call with the value. You do not explicitly have to worry about that. Go takes care of it, so that this syntax is pretty readable. Because if you compare, if we had to do this p dot scale, if we had to do this, then it looks very ugly as compared to just p dot scale. So that's why, depending on your use case, depending on the context that it is getting used, Go automatically converts this instance whether to a pointer, or if it is a pointer then to a value, using either %p or star p, depending on whatever the signature of the receiver is, so that the program is more readable. That's all it offers. It makes the program more readable by automatically referencing and dereferencing the pointers. Now the question is, when do you use pointer receiver and when do you use value receiver? How do you make the decision? So there are two things that can help you choose whether to go with a pointer receiver or to go with a value receiver. First, if you are mutating any value in that struct instance or into that type, it can be struct, it can be an integer, it can be a float, string, anything. If you are doing any kind of mutation and you want that mutation to reflect on the original instance, if you want the result of the mutation to show everywhere that struct is being used after calling the method, then use the pointer receiver, because using a pointer will actually change the value. Otherwise, if you use a value receiver, it will just create a copy of that and pass it to the method instead of passing the actual variable, instead of passing the actual instance of the struct. Second thing, if it is a very large struct, if it is a huge struct, let's say fields of hundreds and like 50 or 100 fields, in that instance, if you call the same method again and again on that struct, then Go internally has to assign memory locations for all those fields. The fields can be slices, the fields can be other structs, other arrays, integers, floats, complex, any kind of data type, and it has 50s and hundreds of fields. In that scenario, every time you call the method, it has to create a copy of that struct and pass it into the method. So that is a little expensive. Now, it is not a huge performance degradation, but it still affects your system in some kind of way. So if you know explicitly that the struct is very large and you want to avoid making copies again and again, then in that case, go with pointer receiver. Otherwise, go with value receiver. So those are two thumb rules that you can use. Now, the last thing to remember is, once you make some method, for instance, we have scale method on this. For this, we want to mutate the instance of the struct. That's why you are using pointer receiver. Now, after this, we want to define another method called ABS. Now, ABS returns a new value. It does not mutate the existing instance. But since we already had a method which was pointer receiver, after that point, we cannot, or we can, but we should not use value receiver anymore. we cannot use value receiver anymore once we define a method with a pointer receiver. So the convention is either make all the receivers pointers for all the methods of a particular type, or make all the receivers values. Do not mix. If you mix, very bad things happen because of very subtle bugs that we will see later. But this is something to remember. Once you make one receiver pointer, you have to make all the receivers pointers. Otherwise, bad things happen. Okay, just remember these 3 rules. If you are mutating, go with pointer receiver. If you want to avoid copying a large struct, go with pointer receiver. Or if you made one method a pointer receiver, always go with pointer receiver for all the methods. Those are the 3 rules to remember. And those 3 rules will help you to decide whether to go with pointer receiver or to go with value receiver. Now, in order to understand methods with a real world example, we are in the FIDER open source repository. Now we have a struct here, whose name is user, and it has different fields. It is most probably coming from a database. Okay, that's why it has ID, name, tenant, email, role providers, and all these things. And we have different types, and we have JSON tags to parse it properly. Now, the thing to focus here is, for this user struct, they are defining, right, some methods. And if you take a look at these methods, so this method has provider. What is it doing? It is taking an instance of user. Whenever you call a user struct, an initialized user struct, with this method, it will pass the instance of that user into this method, and it will have a argument for the provider string. And what it is doing, it is ranging through all the existing providers of a user. So we have an array of providers inside for this user struct. It is ranging through, it is looping through all the providers, and if it has an existing provider with the same name that we are passing here, then it returns true, otherwise it returns false. Now, for this, if you can ask a question that there is no mutation happening here, then why are they using a pointer receiver? Now, there can be multiple reasons, and we won't know it for sure unless we read the whole code base, but we can take some guesses. We can take a guess that maybe the struct is very large, or there is another method on this user struct somewhere that mutates the user instance, and because of that they had to use the pointer receiver, and after that point they had to make all the receivers pointer receivers. So as I said, you have to either make all the receivers pointers or values. You cannot mix and match. So the reason can be anything, and we won't know unless we read the whole code base. So for now, let's just focus on the methods and why are they used, and get the feel of it. Why are we declaring methods on this user struct? In the same way, there is a method called isCollaborator, which basically checks whether this user's role is a collaborator role or it's an administrator role. In the same way, administrator is another method, and it checks whether this user's role is a administrator role. Now, by looking at these examples, you can take a fair guess that why methods are important. So if we did not have methods, if we did not have the concept of method, what we would do, we would declare different utility functions. So we can say we declared a function called user has provider, or is user collaborator, okay, or is user administrator. And you can see the pattern here, that every time you create a new utility function, you have to explicitly name the function in a way that it is clear that this function is supposed to be used with an instance of the user struct. Okay? Otherwise, it is very confusing if you just create a utility function with the name has provider, and if someone new in the code base, someone new comes in, then there is no way for them to understand that what is supposed to be the scope of this function. Where is this function supposed to be used? And having methods provides this semantic advantage that we have a type user, and a user can have a lot of behaviors. A user can check whether it has an existing provider, a user can check whether it is a collaborator, a user can check whether it is an administrator. And now we don't explicitly have to name the methods is user administrator, or is user collaborator, or is user has provider, etc. Because it is already in the scope of user, and whenever we call it, we will call with user or u dot has provider or u dot is administrator. We have this predefined scope, and it makes things very easy to read, makes things very easy to process, and the flow of the program is much more simpler. So using methods provides a lot of advantages like this, and as you build more programs with Go, you'll see a lot of advantages along the way. Now we have a very interesting concept called interfaces, and interfaces are something that is very deep into Go's philosophy, and you'll find interfaces everywhere in the standard library, in all the packages, and it's a very important concept to understand. And for now, as long as you understand the basics of it, even if you don't understand completely, it's fine, and we'll use interfaces in our projects, and when we are reading code, we'll look at a lot of interfaces and we'll see how they work. So for now, let's just understand the basics and move on. Let's not spend a lot of time here, because interfaces can be a little tricky to understand in the first look, and you get the feel of it as you work with it more and more. Okay, so let's understand what's happening here. For now, we have a type here, and it is not any other type. It is not a struct or integer or string, anything. It is of type interface. Now, what goes inside the interface type? Inside the interface type, we have methods. We have method signatures. That's all there is to it. Two interfaces. We have interfaces, and inside that we have method signatures. Now, how do they work? How are they useful? To understand that, let's dive into the example. Here we are declaring a variable of type interface, of type this appser interface. We have a variable of type appser interface. Then we are declaring another variable of type myfloat. This type is here, and since the order does not matter where you declare the type and where you use it, we can declare the type later after the main function. So we have a type here of myfloat, which is of type float64 internally. This is a user defined type. Okay. Now we are using that type here, and we are initializing it with this predefined function. And if we hover over it, we can find the value of the function. It is some floating point value. Now we are initializing a struct of type vertex, and if you take a look at below, we have a struct called vertex, and this vertex struct has a method assigned to it. Its name is ABS, and it takes a receiver of pointer to vertex, not the value, pointer, and it does some calculations. In the same way, for the myfloat type, which is the float64 type, we have a method which calculates the absolute value and returns it. We have two methods, and for this we are using value receiver. We have a myfloat type, we have a vertex type. This is struct, it is a float64. Now going back to this, what we are doing, we are initializing a vertex type. Now what we are doing, we have a variable A which is of type this interface. Now we don't know what interface does yet. We just know this is of type this interface. Now to this variable we are trying to assign f, which is of type myfloat, and it works. We don't get any error. Ignore this yellow line. There's some linting error, but we don't get any error here. We can assign the type myfloat to the variable A, which is of type appser. Now, if you remember, initially I told you that since Go is a statically typed language, we cannot assign one variable of one type to another variable of another type. We have to explicitly convert the type. But here, we are not converting myfloat into appser, which is of a different type, even though it's an interface type and we don't know what it does, but it is of a different type in Go, and it should throw an error, but it is not throwing an error. We can assign f to A. That is the first thing to notice here. Second, we are taking v, which is an instance of type vertex, which is struct, and we are assigning the pointer of that variable to A, and that also works. We can assign it to this. But now here we see the behavior. When we try to assign v instead of the pointer to v, when we try to assign v itself to A, we get an error. And if we hover over it, it says cannot use v, variable of type vertex, as appser value in assignment. Vertex does not implement appser. Method apps has pointer receiver. Now this is the important part here. Vertex does not implement appser because method ABS has pointer receiver. Now we can assign pointer to v to A, but we cannot assign v, which is of type this struct, to A. Why? Because pointer to vertex has a method called ABS, but it is a pointer receiver. It is not a value receiver. That's why we can assign a pointer to vertex to A, but we cannot assign a value to A, because only the pointer implements this method. This method is assigned with the pointer receiver, not the value receiver. That's the reason we cannot assign the value to A, which is of type interface. Now, on a high level, what do we understand from this? What do we understand from this? We understand that an interface type basically provides some kind of behavior that a type should have to implement that interface. This is what interface means. An interface basically gives you a signature, that this is the signature that a type should have to implement that interface, to say that that type satisfies this interface. Unlike other programming languages where we also have abstract classes and we also have interfaces, where in order to use them we have to explicitly write things like implements, or we have to explicitly use some kind of syntax to say that this type implements this interface. But in Go, the speciality of Go is that as long as there is a type myfloat, and it has a method whose signature and whose receiver matches that of the interface, then we can say that this type implements appser. Since interface has a method whose name is ABS and its return type is float64, in the same way myfloat has a method it's a concrete method, and it returns a float 64 and it matches this signature. That's why we can assign an instance of my float to a variable which is of type this interface. Okay, now my float satisfies absent. That's the word to remember. My float satisfies an interface as long as it has all the methods that this interface defines. It does not have to do any kind of explicit mapping to the interface. It is implicitly satisfied. So that's a very important concept to understand. An interface in Go is implicitly satisfied by other types as long as they have those methods assigned with them. Now we could not assign the variable v to a because in here the method is assigned with a pointer receiver, and since now v was a value here, we could not assign v to this. That's the basics of interface. We use interfaces to provide some kind of abstract signature beforehand or afterhand. It does not matter. It is an abstract signature that a type can satisfy as long as it has all the methods assigned to them that the interface provides, that the interface asks you to implement. Now here in this example, we have a struct of type t, and it has a value which is called s, and that is of type string. And we also have an interface type. This is basically a set of rules. We have a set of rules that any type which has a method called m assigned to it will satisfy this interface. That's what it says. Any type which has a method called m assigned to it will satisfy I. It can be assigned to any variable whose type is I. Now t struct has a method called m, and it is doing some basic printing. It has a value receiver, and now here we are declaring a variable of type I, not of type t. We are declaring a variable of type I, and to that variable we can assign a struct of type t. We can assign it a struct of type t to a variable whose type is the interface I, because t implicitly satisfies the interface I because it has a method called m and it satisfies this signature. And now after this we can call the method m using this variable I, which is of this interface type I. That's how interfaces behave. Now there is some theory to understand here, that what exactly is an interface type, what does it exactly consist of. M using this variable I, which is of this interface type I. That's how interfaces behave. Now there is some theory to understand here, that what exactly is an interface type, what does it exactly consist of. So you can think of interfaces as some kind of containers, and that's what they are. Interfaces are basically containers which have two properties. One is dynamic type and the second one is dynamic value. Okay, and an interface itself, let's say when you declare a variable where I of type interface I, when you do this, we already know that whenever we declare a variable in this way, Go assigns the zero value of that type. And what is the zero value of an interface type? It is nil. Zero value of an interface type is nil. And when you do this, you can actually call the method I.m here, because an interface has a signature and it has a bunch of methods that you can call on that interface. But in order to call those methods, an interface has to have these two properties inside it. Only after a concrete implementation of that interface is assigned to the variable of that interface, after that only we can call these methods, and after that only it will be valid. Because an interface, when you declare an interface in this syntax, it is an empty container. It is of type nil. It does not have a dynamic type. It does not have a dynamic value. But in this case, when we assigned the type t, we assigned t, which is a struct. When we assigned an instance of the struct to I, when we did this t hello, only after we did this, then we were able to execute this method I.m. And what it did was, after you assign this instance of the struct to the interface, now this container is not empty anymore. It is not nil anymore. Now this container has two things. One is a dynamic type. That dynamic type is this struct. This struct type is this interface's dynamic type. This of type t, and its dynamic value is that instance of the struct which has this field called hello. And now the interface is not empty anymore. Now you can call methods on this interface and it will work as expected. But what happens when you declare an interface and you call it right away without assigning a concrete implementation of that interface? What happens when you call it without assigning a concrete implementation? Now let's test that and confirm our theory. Here I have declared a variable of type I. I is an interface which has a method. Now the program will allow us to call this method m on this interface because it has a signature and it has the method m. But when we call it, when we run this program, we get this error. Which says this. It says nil pointer dereference. We are basically trying to access a memory location which does not exist. It happened because interface, at this point interface is empty. It does not have a concrete implementation. Only after we do this only after we assign a concrete implementation which satisfies that interface because of the same method signature. Only after we assign it to this variable, then if we call the same program, then we can see hello. What it does, the interfaces behind the scene, it tries to access this type of type T, then it accesses this field and it passes this receiver and it calls this function and we see it in the console. Okay, so basically interfaces are just containers. They provide you with some behavior that you have to satisfy, but they themselves don't have any data. They have to be assigned some data. They have to be assigned a concrete implementation before they are usable. If you call it before that, it will be an error. Your program will panic and it will break. That is something you have to remember. Now, I said before that interfaces are everywhere in Go, and because of the nature of an interface in Go, because of the nature of satisfying behavior, we have a very useful construct which is called an empty interface. This is a type which is called an empty interface literally. Now, what is the property of this type? What is the behavior of this type? When you have a variable or when you have a parameter of this type, you can assign anything to this variable. The Go static type system will not stop you anymore because it is an empty interface, and as we already know that an interface is satisfied as long as you have all the methods that the interface asks you to implement. And since an empty interface has no methods, it has 0 methods, then any value in the Go's type system, any type satisfies this interface. That's the reason we can assign any value to a variable of type empty interface. And that's what we are doing here. We are declaring a variable with type empty interface, and we are assigning different values. We are assigning a string here, we are assigning a value here, and it all goes through. It does not stop us. In fact, if you take a look at the signature of printf, it says ... any, which means you can pass any number of arguments. It is a variadic function, which means it can take any number of arguments of type any. Now, any is basically an alias for type interface. So if you take a look at Go code, this is how any is defined. So you have type any, and it has interface. So any is just an alias for interface to make things a little easier to write. Okay, and all the print statements use the empty interface or the alias any to take any number of arguments of any type. It does not matter what the type is, they take anything. That's why they are using empty interface or the alias any. Now, when you use this empty interface construct, then you want to assign any value to a variable. In some cases, it might be useful, but when you actually want to use it, since it's empty interface, you don't know what exactly is the value inside it, what exactly is the type inside it. And since Go is a statically typed system, it will not let you use the variable until the empty interface or the alias any to take any number of arguments of any type. It does not matter what the type is, they take anything. That's why they are using empty interface or the alias any. Now, when you use this empty interface construct, when you want to assign any value to a variable, in some cases it might be useful, but when you actually want to use it, since it's empty interface, you don't know what exactly is the value inside it, what exactly is the type inside it. And since Go is a statically typed system, it will not let you use the variable until it knows what type it is. And to confirm the type of a variable, which is of type interface, it can be any interface, we have this feature called type assertion, which is basically a way to cast a value of one type into some kind of interface. It is basically checking whether this type is of this type, whether this interface is of this type. Okay, so let's just look at this example to understand this better. What's happening here? We are declaring a variable which is of type empty interface, which means we can assign any value to it. It can be string, boolean, number, anything. And here we are assigning a string here to this variable. At this point, what we are checking, this syntax I dot and a type name. This syntax is basically saying whether I, this variable I, is of type string, whether this variable I is of type string. If it is of type string, it until here it says interface, but after the type assertion we have the type string here, and if you print it you will get the result. And in order to check, in order to provide some kind of assurance that this type assertion was successful or it was failure or this variable does not satisfy this type, in order to provide that mechanism, this type assertion provides two values. The first is the new variable which has the type this, the type that we are trying to assert to, and a second variable which is a boolean which says whether the type assertion was successful or not. Okay, and using this you can check the value and the success or failure. What happens if you use a type assertion? What we are doing here, we have a variable which has a type empty interface, which means any value can be assigned to it, and we have assigned a value string to it, and we are trying to convert a string type to a float type, and we are asserting this type. We are saying if this variable is of type float64. We are also doing it here, but here we are doing it without this boolean. Now, if you do it like this, the program does not break, the program does not panic, it does not error out. We have an OK which is false because a string value cannot be converted into a float value in any way. But in this case, we are not taking the boolean. So the behavior in this case is the program panics. If you're not taking a boolean in the second value of return type, then this program will error out. And if you try to run this, this. It is not a compile time error, it is a runtime error. Then we see the results here up to this point, but when we execute the last statement, we get a panic because we tried a types assertion without taking the variable OK, without taking the result of the variable, whether the result was success or it was a failure. Now, to assert to this type again and again is a little cumbersome. That's why Go provides a very nice construct for us to systematically check a list of types that we want to satisfy to, and if it matches one type, then we can perform whatever operations that we want to perform on that type. So for that, we have this example. Here what we're doing, we have a switch statement, and in the switch statement, we already know that in the initial part of a switch statement, we can call an expression. So it is calling this expression and it is doing a type assertion. So this is basically a type switch. This is something you'll find a lot whenever empty interface is used. And this is a type switch. What it is doing, it is trying a assertion here at this statement, and this type, the actual type of this variable, this I, will be assigned to V. And then we are checking different cases. We are saying find out the type, the dynamic type of this variable I, and check whether it is an integer or not. If it is an integer, then come to this and break out of this switch statement. If this is a string, then come to this and break out of this switch statement. If it does not match any of these cases, then come to this and execute this default statement and break out of the switch statement. And then what we are doing, we are trying this example where we pass an integer first, then a string, then a boolean. So if we run this, we get different results. For the first one, we are doing some integer calculations. Since the type here satisfies integer, we can do mathematical calculations here. Until this point, we cannot do anything with I. We cannot do anything with I. Let's try to do something here. So this point, we don't know the exact type of I. So if you do this, I equals to I plus 2. If you do this and if you hover over it, it will say invalid operation, I plus 2, mismatch type interface and integer. Basically saying you're trying an integer operation on a type which is of type empty interface. You cannot do that. Okay. And in the same way, if you try to call length on I, if you hover over it, it will say invalid argument variable of type interface or built-in type length. You cannot call length on this type interface. Basically, you cannot do anything with this type unless you cast it explicitly to some type, some basic data type or to some complex data type, anything. You have to explicitly cast it to some type. Since Go is a statically typed language, you can use this construct. You can use this empty interface to pass a value of any type. But when you want to use this, when you want to use that value, you have to explicitly assert it to some type. It can be integer, string, boolean, or anything. And a type switch is a very nice way to conditionally check different types and to perform different operations depending on that type of this value. And as you can see that in the first function call, it was an integer, that's why it landed here. In the second one, it is a string, that's why it landed here. And in the third one, it is a boolean, that's why it landed on the default case because we were not handling boolean. Okay. And now since we know about interfaces and we know about type switches and different types of dynamic types, there is a concept that is used heavily across the standard library of this interface type, which is called stringer. Now there are two things to notice here. First, in the standard library or in different places where people are using interfaces, you will see this pattern that all the interfaces are ending with this suffix er. It's a stringer or a printer or a downloader, something, a er suffix, because of the behavior. Because interfaces define a set of behaviors, this er thing, this er suffix conveys that emotion more explicitly. So this is one thing to notice here. Second is, the stringer interface is defined in the standard library. So this is what it looks like. Let's clear this. We have a type in the standard library which looks like this, type stringer, and it's an interface. It starts here, and inside that there is one method. It is called a string method. Okay? And this is an interface which is defined in the standard library, and it is used heavily everywhere. Basically, a type. It can be any type. It can be a struct, or it can be a user-defined type of type integer, float, string, anything, a map, anything. Now, that type is called to be a stringer. It's called to be implementing stringer as long as that type has a method called dot, as long as it has a method called string. Now, it is important because in the previous example, we saw that using a type switch, we can check that whether a variable satisfies an interface or not. Okay, we can check that. So, in functions like this, in functions like sprintf and printf and println, if you take a look at this, they take variadic arguments of type any, which is an alias for type interface, empty interface. Now, they demand that whatever you pass, they can be any value. They can be any value. That's the reason they have said any, which is an empty interface. They can be any value, but they have to satisfy the interface stringer, which means they have to have a method which is called string. So in this example, we have a struct. And it has a method. What this method is doing, it is taking the instance of the struct and it is printing the name and the age using %v. Basically, it has a string method which represents this struct in a string format. That is the reason we can take this instance of the struct and we can pass it to println, because now this struct satisfies the interface stringer, which this println, printf, sprintf functions require. They require your type to implement the stringer interface, which means your type has to have a method called string. Now what happens if you comment this out? What if you run this? Now if you run this, they use its internal representation. Since this type does not implement stringer interface anymore, they have some default representation of how a struct should look like, and that's how they're printing it. Okay? They don't follow this format anymore. But if you uncomment this and if you run this again, now if you see this format, matches this method, because when you pass any type to println, what they do, they check whether this type implements stringer interface, which means whether this type has a method called string. If it does, then they call that type's string method. If it does not have a string method, that's when we commented it out. It will use the default representation of the any struct that Go has internally. Okay, so that is another thing to keep in mind. Now we have another interface, a very famous interface, which is called error, and you will see this everywhere in Go. This statement: if error is not nil, do something. If error is not nil, do something. Since Go follows this principle of explicit error handling, it follows the principle of explicit error returning errors as values and all these principles related to errors. Go has an interface called error, and it is an interface. And since we know the zero value of an interface is nil, that's the reason we can check that whether it is an empty interface or if there is an error in that, or if there is a concrete representation of some type which satisfies error and it is present in that. And let's look at this example to make this more clear. Now, here we have a type struct which has two fields, when and what. When is of time.time, there is a package called time, and it is of type time of Go of time. There is another field called what, it is of type string. Now, this struct has a method associated with it called error. It's called error, and it takes a pointer receiver and it prints the when and the what with using fmd.sprintf. By the way, sprintf basically it does not print the formatted string into the console. Instead, it formats the string and it returns it if you want to return it. It basically constructs a new string. It does not print it or anything. That's why you're using sprintf. That's what this error method is doing. Then we have this function run, and it basically returning an instance of this struct with these two values, time.now, which basically takes the current time, and string call, it did not work. And in the main function, we are executing this function, and if it returns an error, in the signature we are saying this function returns an error. We are executing this function, and we are saying in the signature that it might return an error. That's why. And it returns this error type. And there are some things to notice here. First, we are declaring a custom type, which is called myError. But when we are returning from this error, it is not a myError type. We are returning a generic interface called error. Now, error is another interface like stringer, which is defined in the standard library of Go, which is provided by Go, and it looks something like this. It looks like this: type error, and it starts, and inside that it has a method called error. As long as any type in Go, does not matter it's a struct, integer, float, string, map, does not matter what type it is, as long as that type has a method called error like we have here, it is of type this interface. It satisfies this interface error, so we can use that type in place of this type. That's what basically interfaces do. As long as you satisfy the signature of an interface, you satisfy the requirements of an interface, you can use your type in place of that type, in place of that interface type. So having that in our mind, this function, this run function, it says in the signature that it is returning a type of error. It is an interface, but it is returning a concrete type. It is returning a type struct, but that struct has a method called error, and it is doing some kind of formatting, string formatting. And now the reason we are returning an interface instead of saying in the signature, instead of saying the return type is of type myError, the reason we are returning an interface is because of this. When the caller, the function that is calling this one, the main function, it calls run. When it calls it, it checks whether the value of error is nil or not. And since we know that an empty interface has the value nil, since we have this knowledge, since this is the fact, what now we can do is every time we run a function, if that function returns an error, then we can check if the error is nil or not. Since it is an interface, if it is not returning an error, if it is returning nil, then this case will be false, and we will proceed in the success flow. And if it is returning some value, it does not matter what value, it has to satisfy the error interface, and it returns some value, some concrete implementation, then the error is not nil. In that case, we will succeed with the error flow. Those are two reasons we use error interfaces everywhere in our program. So that's all about interfaces that we need to know as a basics to start out writing more programs. Now, there are a lot of different behaviors to interfaces, and there are a lot of concepts associated with interfaces that we will explore as we learn more, as we read more code, as we write more code. But as of now, that's pretty much all you need to know. Now let's take a look at some examples of how people use interfaces in real-world apps. Now going back to our example, you can see there are interfaces everywhere. We are using interfaces to define behaviors, to define methods, get email, get name, get user, get kind. Interfaces are used to define behaviors everywhere in the code base. Now there are a lot of different use cases associated with it. One particular use case that interfaces have in a real-world app, in a backend app, is when you are writing test cases. As we know that in backend systems, we have different layers of system. We have, let's say, in the base layer, we have repositories. Repositories. Above that, we have services, and above that, we have controllers. Repository layer basically deals with all the database operations, all the database queries and inserts, removing all these core database operations. And the service layer uses this repository layer to mix and match different business logic with different repository methods. So it can execute some repository method like create an entry in database. Then in the service layer, it can send an email, it can send a notification, and it can schedule a task. All these things are responsibility of service layer. It basically orchestrates different repository methods with business layer. And then there is the controller layer, which deals with HTTP related stuff. Like it receives the body, it receives the query parameters and all, it parses it, it validates it, and it passes on all those input arguments to the service layer, and whatever things that are returned from the service layer is passed on to the controller layer, and it sends those responses appropriately with appropriate HTTP status codes and appropriate data format, and etc. etc. That's the overall flow looks like in a typical backend layer. Now, some backend system might not have a service layer, the controller might use the repository layer, but it's just all about terminologies. Typically, we have 3 layers. Now, we have this repository. This is an open source repository called Incubator Answer, and you can take a look at it. This has very good patterns that you can learn from, and scalable patterns, scalable backend patterns that I personally use to learn a lot of stuff. So anyway, we can see here that there is an interface here. We have an auth service, basically a service which don't need to understand any of the code, just focus on what I am explaining. Okay, we have an auth service which basically deals with different operations related to authentication. Okay. We have an auth service. It's a service layer. Above that there is a controller layer. Below that there is a repository layer. Now, this auth service in argument in its parameter to initialize this auth service. Go has a very good dependency injection convention. We will explore more about dependency injections and all in later videos when we are building projects, when we are reading different project codes. Now, what dependency injection basically means, instead of directly importing the auth repo, you take the auth repo implementation as a parameter, and then you return this instance of auth service which has all these methods. So this is a struct. A struct has different methods associated with it. If you scroll down, this is all these methods in this user service struct. Okay, we have explored methods just a while back, so you should have some idea that what's happening here. And what's happening, it is taking an implementation of auth repo, the repository layer for authentication, and it is returning a service, auth service, with auth repo inside it. That's what's happening here. This is a constructor, you can say the initializer of this auth service struct. Now, here auth repo is not a concrete implementation. It is not coming from a struct. This auth repo is actually an interface that is declared in the service layer itself. There is one convention when you are dealing with interfaces, when you are declaring and using interfaces, which are always, interfaces should always be on the consumer side. Now, of course, there are exceptions to it, very valid exceptions, not very rare also, but it's a general thumb rule, a very